Chris. Okay, thanks very much. This is my first time in the Netherlands, so I'm very happy to be here. I was just in Utrecht yesterday, so it's kind of a lightning tour because I'm leaving tomorrow. Perhaps I'm just getting old, but it seems like I'm like twice the age of everybody in this room, except maybe gosh. So I'm guessing you guys are students. Many of you are students, and if you have any questions, don't hesitate to interrupt me while I'm giving the talk. Don't wait till the end if there's something that's confusing. So the whole point of the lecture is to communicate knowledge to you, not just for me to talk to myself. So don't hesitate to ask questions. This is actually quite an esoteric subject, so questions are quite likely to come up. Okay, great, thank you. All right, so here are some references. The slides I'm using are available in PDF format, and in the actual PDF, all these are clickable links. So if you get the PDF from me or from the organizer, you can find all this information yourself. Most of what I'm going to talk about is in these two relatively recent papers from earlier this spring, one in Phys Rev Letters, one in Physics Letters. There is an earlier colloquium that I used to give on this topic, which is at a very kind of pedestrian level. So if you're interested in more of the background about the black hole information problem, I suggest you look at the colloquium. The two review articles that I suggest on this topic are by Subrat Raju, who I'll say a little bit more about the perspective of his perspective and that of his collaborators on this problem. It's very similar, I think, to what I'm going to say. And the other review article I recommend is older. It's about 10 years old, and it's by Samir Mathur at Ohio State. And he gives what I think is the conceptually cleanest formulation of the black hole information problem. And I'm going to specifically, in the latter part of this talk, address his formulation of the paradox and how our proposed solution actually finds a loophole in his theory. Okay, so I put this slide here at the beginning for impatient experts. So if you're not an expert on this subject, just ignore this slide, but this gets some of the urgent questions that some people tend to have out of the way. So probably some of you are familiar with ADS duality. The idea is that you have a bulk theory of gravity. It's dual to some boundary theory. That boundary theory might be a CFT or some kind of gauge theory. And since the discovery of this kind of duality, I think people have had the general idea that because the boundary dynamics is presumed to be unitary, that means that somehow the black hole evaporation is also unitary. But of course, the specific details of how the information gets out of the black hole or from behind the horizon has been lacking. More recently, there's been work on something called information holography. That's, I think, terminology due to Raju. The idea there is similar, it's related to A, but it's different in some important respects. The idea is that if I look at configurations in the bulk, including a black hole, the quantum state of the long-range gravitational field, so in particular, even at the asymptotic boundary of the space-time, contains all the information about even what's behind the horizon. So it's information holography. It's not a statement about duality between dynamics, but it is a statement about what one could in principle recover from measurements at the boundary of the space-time. And this idea B is similar to what we call in our paper quantum hair. So the idea that there is something about the quantum state of the gravitational field of a compact object that contains all the information about that kind of compact object. So A and B together both suggest strongly that black hole evaporation can be unitary. B implies also the existence of quantum hair. However, neither A nor B reveals how the information is actually really encoded in the Hawking radiation. That's what I'm going to spend a fair bit of time talking about. Okay, so this problem that I'm going to talk about has been open since, I guess, about 1976. A little history lesson for you guys. I mean, you're so young, probably a lot of you weren't even born then. Well, none of you were born then, probably. So at first, people didn't take this paradox very seriously. It was only in the, I'd say, 80s when a few people did, and then 90s when people started thinking about it seriously. And here I have a list of various models of gravity, quantum gravity of increasing sophistication. So at first, just Newtonian gravity, and then classical general relativity. Then the next step might be to consider the propagation of other quantum fields in some curved space-time background. And then finally, the idea that one actually has to take seriously the quantum state of the graviton field. Now, at each of these stages, one could do some kind of theoretical calculations which would point to interesting things which would only be resolved at the next level of sophistication. So already with Newtonian gravity, people like Laplace noticed that you could have an object so dense that the escape velocity would exceed the speed of light. And so you could have, they didn't use the term then, but a black hole. With general relativity, you could find classical solutions of the Einstein equations, which actually describe the full spacetime of a black hole. In that background, one can then compute the propagation of quantum fields. That is how Hawking discovered Hawking radiation. And then you had the idea that black holes could evaporate. And almost immediately, once you realize that, he proposed that there's actually a kind of paradox in that the information that falls into the black hole somehow doesn't seem like it can get out in the form of the radiation. At the end, if the black hole fully disappears, it seems like some information was lost. And the focus that I'm going to take in this talk is at this level of thinking about gravity. And we're going to use only long wavelength, low energy properties of gravity. So we're not going to propose anything about the UV completion of quantum gravity, but we are going to show that properties of the low energy effective theory of quantum gravity probably are enough to actually solve this problem, enough to state the problem and actually enough to solve the problem. Okay, so when you look at the classical black hole spacetimes, there's already classification of those spacetimes in terms of certain conserved quantities that the black hole can have. And this terminology actually is due to Wheeler. So Wheeler coined the term black hole, and then he also coined the phrase black holes have no hair. And maybe not no hair, but limited kinds of hair. So if you look at the asymptotic behavior of a black hole spacetime, you can ask what properties of the black hole are discernible just from the classical fields at long distances. And of course, you can measure, for example, the ADM mass, you can measure the angular momentum of the black hole, you can measure the total charge of the black hole. Now, the idea that the no hair theorems are themselves purely classical. And the question has always arisen, at what level do these no hair theorems persist when you actually quantize a gravitational field? And people have always suspected that there were some small modifications of the no hair theorems due to quantization of the gravitational field. But actually what we're going to say today, and what Raju has been saying in recent years, is actually quite a bit stronger. It's that one can actually recover the information about the compact object, which is the source of the quantum hair, through in principle measurements of the quantum hair itself, the quantum state of the gravitational field. Okay, so the idea of a black hole really has to do with the way it modifies the causal structure of the spacetime. These are familiar light cones, so particles can only move forward in time inside this forward light cone. I have a star collapsing here, and then once the star forms a black hole, you can see that the light cone, which is a function of its position on the spacetime manifold, when you're inside the horizon, the light cone is tipped over to the point where the future of any particle that's inside this horizon must include the singularity. So at least at this classical level, any particle which passes through the horizon has in its future meeting the singularity. Okay, so once you realize that's a property of the spacetime, one can ask questions about quantum fields propagating on that spacetime. So one could consider, for example, vacuum fluctuations, which are close to the horizon. And you could imagine a situation where you have, say, an E plus E minus pair. One of the entangled pair goes behind the horizon, ends up hitting the singularity in the future. The other one perhaps escapes to future null infinity. And so that carries away some energy. And that particle that escapes to infinity is a quantum of Hawking radiation. Okay, so this was first discovered by Hawking. two phenomenological properties of this Hawking radiation is the temperature is extremely low. It's 1 over the Schwarzschild radius in Planck units. Because the temperature is so low, what you really have is very intermittent evaporation, very intermittent emission of the individual Hawking quanta. So it would emit something, and then a very long time might pass before the next one is emitted. And the total lifetime of any kind of macroscopic black hole is many, many times the age of the universe. So this whole phenomenon is very low energy, very long wavelength, and the whole process takes place over an extremely long time scale. Okay, so here I've got a Penrose diagram of an evaporating black hole. And what it shows is the collapse of a star, formation of the black hole. And if you recall, in the Penrose diagram, light-like particles move at 45-degree angles. So a photon from the distant past can come forward in time and hit the star. It can come forward in time and hit the black hole. It can come forward in time and pass through the region of the black hole long after it's evaporated. Okay. And the dotted line here is the world line of a specific external observer. And so at point A on this world line, photons from the star can reach him. So he can see that there was a star. At some later time, B, he can see the Hawking radiation, which is coming from the now formed black hole. And then at some later time, late time C on his world line, you can see that the black hole is completely evaporated. Okay. And one way of stating the paradox, I'm going to state the paradox in successively more sophisticated formulations, but really one of the first ways to state it is that, well, this Hawking radiation seems to originate in fluctuations, vacuum fluctuations, which are outside the horizon. We already said, looking at those little light cones, that anything outside the horizon is causally disconnected from things which are inside the horizon. So if the things inside the horizon can't influence this Hawking radiation, then how can this Hawking radiation carry away to infinity the information about what was in the black hole? So that's probably the simplest way to propose the paradox. As I mentioned, Hawking did this in 1976, and a more sophisticated way of describing the consequence, rather than saying information is lost, is to say that a black hole causes a pure state in quantum mechanics to evolve into a mixed state, which is not supposed to happen. Okay. Here I have a slightly more sophisticated formulation of the paradox. This is something that became predominant, I guess, in the 1990s. And in a way, it's related to the question of how does the future state of the universe depend on the past state? And if the universe is a closed system and we're just doing quantum mechanics, then one should be able to take the final state and time reverse it and get back to the initial state. Otherwise, you have a problem with unitarity. Now, these blue lines are space-like slices. So you can regard, at least there is an A-coordinate system in which you can regard all the points on any one of these blue lines as being at the same instant in time. So simultaneous. Okay, so you can think of this as one moment in time, it's another moment in time, it's another moment in time. And so as we go through from space-like slice to space-like slice, we're foliating the space-time, and time is progressing in the forward direction. Now, there is a particular set of these space-like slices that came to be referred to as nice slices. And nice slices are chosen so that they intersect all the stuff that fell into the black hole or formed in the black hole, but then they also intersect all or almost all of the Hawking radiation which comes off of it. Okay. So there is a coordinate system in which the stuff that's inside the hole is existing at a space-like separation from all of the Hawking radiation, or almost all of the Hawking radiation. And the observation was at the time that due to something called the No Cloning Theorem, the exact quantum state which exists here cannot also exist here. Otherwise, that would violate the No Cloning Theorem. So there's no unitary evolution that can produce an exact copy of a particular quantum state somewhere else. Okay, so that's another way to state that the existence of black holes or the existence of space-times with this causal structure lead to a kind of fundamental problem for quantum mechanics.
Sorry, can I ask a question?
Yeah.
But that part of the Hawking radiation that you're seeing on the same time slice as the black hole itself originated from a previous version of the black hole, so it's not exactly the same information because the black hole evolved in the meantime.
Correct. So the statement is the whatever the quantum state is here cannot be replicated here.
Yeah.
That's the statement.
Is it a problem if you take into account the fact that that Hawking radiation is not kind of exactly contemporary to the black hole?
So the question is whether you can, so if I then follow this thing and I follow, like I keep pushing these blue space-like slices forward in time. The question is whether, let's suppose I have now one that kind of hugs future null infinity. Okay, so that has intercepted all the Hawking radiation that came from the hole, and there's no more hole. Okay, the question is whether you could evolve that, just that pure quantum state backwards in time and recover the pure quantum state here. And the claim is that you can't because this information is missing. Does that make sense?
Yeah.
It's clear that or it seems like if I evolve this slice backward in time, I can get back to this slice, but I needed what was here to do that. But then the argument from no cloning is what is here cannot also be here.
But wouldn't it be just a bit above on the next space-like slice?
Well, not really. So let me say it this way. If I take this full quantum state and I evolve it back, I get this. But if I tell you that you can't have this information here, and it's this which gets pushed up to here, then this evolved backwards cannot reproduce that.
Okay.
Does that make sense?
Yeah.
This is that. By the way, this is still not the best formulation of the paradox. We're going to get to a better one. So, but this is the way people are thinking about it, say between 1990 and 2000. Okay. Now, all of these, if you think carefully about it, all of these formulations of the information paradox, they assume a fixed classical background geometry. So I said it's a certain level of sophistication. You find some classical solution to the Einstein equation, and then you talk about quantum fields evolving on that background, but you treat that background as just a completely classical thing, which is given. And of course, we expect that there are some quantum fluctuations in the gravitational field. That means there are quantum fluctuations in the space-time geometry itself. And when we talk about things like A is causally separated from B, we have to be very careful because those are statements you can make very clearly when the space-time is classical. You maybe cannot trust the conclusions when the space-time is actually fluctuating in quantum mechanical. Okay. So now we're going to talk about the quantum state of the graviton field, which is sourced by some compact object. And that's something I claim actually, which has not received a lot of attention, actually, among theorists. Okay, so let me summarize this. This is the first paper, the Physical Review Letters paper that we wrote. And let me just summarize the results, and then I'll get into them in more detail. So one thing to show is that if you take a compact source and you treat it fully quantum mechanically, so there's some Hilbert space describing that compact source. It could be a rock, or it could be a dust ball. We actually specifically look at dust balls. You have some object, it has some Hamiltonian, you diagonalize that Hamiltonian, it has some energy levels, and suppose that it's in some energy eigenstate, some specific energy eigenstate with some specific energy eigenvalue of its own Hamiltonian. We can ask, to what extent is the quantum state of the gravitational field, which that object sources, sensitive to the specific choice of quantum state? Okay. Normally, when we do general relativity, we say, oh, we have a source, but the source is semi-classical. The source is not treated fully quantum mechanically. We just say there is a source, it creates some T mu nu. Typically, that T mu nu is treated classically, and that T mu nu then leads to some solution of the Einstein equations. If we try to go a little bit deeper and we say, no, we really want to be very specific about the source, the object, and then what can we then conclude about the quantum state of the gravitational field that it sources? And it turns out you can show that the asymptotic behavior of the quantum state of the graviton field of such an object is controlled by its energy eigenvalue. Okay? And insofar as there are no accidental energy degeneracies in the spectrum of the compact object, that means there's actually a one-to-one map between the specific graviton states, which are sourced by the object, and the specific states of the object. Okay, so that's a very well, I don't want to say it's novel because we're the ones who came up with it, but it really had not been considered in a detailed way by people until we looked into it. Okay, and another thing is that a semi-classical matter source then would produce an entangled graviton state. Okay, as a specific example of this phenomenon of quantum hair, we looked at the low energy effective field theory of quantum gravity. So, and I'll explain in more detail what that means. We computed for the specific example of a dust ball that the quantum corrections in that effective Lagrangian, in that effective action, would produce a perturbation to the solution to Einstein's equation, which is of the form r to the minus fifth. So it's a kind of potential that isn't normally there in classical physics, but it's there because of quantum effects, and it has the form of a 1 over r to the fifth potential. Importantly, the coefficient of this 1 over r to the fifth term depends on the internal state of the source. So if you take different dust balls which have the same total mass but have different internal density profiles, the coefficient of this new potential term varies according to what density profile you choose for the dust ball. So it's an explicit example of how if you do treat quantum gravitational effects, you can produce effects which are long-ranged and which contain information about the internal state of the source. Yeah.
But if the source is in a fixed eigenstate, how do you define the entropy of a black hole?
So, good question. We'll come back to that in a second. In this calculation, we're doing effective field theory. So what we have is a teeny new source, and we're trying to solve the Einstein equations. But now we're solving them with this effective action, which has some quantum corrections in it. So for this particular calculation, we do not assume that the source is in an energy eigenstate. Okay, but for the previous remark, your question is important. If you recall the formulation of the information paradox as saying that black holes cause pure states to evolve into mixed states, what that means is that I'm willing to consider the whole universe, including the black hole or the progenitor of the black hole, as being in a specific quantum state. Okay, and then the question is then what happens in its future evolution? So in particular, one could consider in building that pure quantum state, one could use the energy eigenstate basis of the black hole. Go ahead.
But for macroscopic objects, I mean, this table is not an eigenstate of any Hamiltonian, right?
Good,
So
good,
or any simple one. So
good.
Why would you expect that this would be important at this distance?
Good question. So the result is just what we stated. So there is a result related to, okay, take a compact source, which is, okay. I made a little remark there saying a semi-classical object, which is the kind of source you usually encounter, then creates an entangled gravitational state. Okay, and I'll explain that in a moment. But what we think of as typical objects, which are semi-classical, they are superpositions of energy eigenstates where the energy is restricted to some band with some uncertainty. Okay, and so we'll get there in a second. But the point is, for those objects, the result that I stated can then be applied, and then you can write the resulting quantum state of the gravitational field as itself a superposition state. So we'll get there in a second, but it's a good question.
That's about this.
Yeah.
Is it mentioned it knowing about the internal state? So are you saying that corrections to Einstein's equations include something more than just the matter stress tensor?
Yes. So here again, I'll give you more details about this calculation. In this calculation, we're not treating the source object in a completely quantum mechanical way. Okay, we have a source T mu, and we're solving the Einstein equations. Now, normally, if I have two dust balls which have exactly the same mass, in classical physics, they produce exactly the same long-range potential. However, because of these quantum effects, if I just rearrange the distribution of the energy density inside the dust ball, but keeping it spherically symmetric and keeping its total mass fixed, I cause a change at the quantum level in the long-range potential. That doesn't happen in classical physics, in classical general relativity. So this is an example of what we call quantum pair. This particular example is not a case where we treat the source fully quantum mechanically, but we do make changes in the internal structure of the source, which are classical in nature, but they create, because of quantum effects, changes to the gravitational potential which don't exist in classical GR.
So with Gauss-Bonnet gravity, be counted to that form?
I'm sorry, can you say again?
Like something like Gauss-Bonnet gravity, so you have some background direction from gravitation groups.
So everything we're going to do here is in standard classical general relativity. So nothing speculative like Gauss-Bonnet gravity. So maybe it'll, when I get to these slides, maybe it'll be clear what we're doing.
Can I ask a question?
Yeah, absolutely.
It's been a while since I've read that there's a information paradox kind of review, but I believe he has some statements there, like even perturbative corrections to
Yes. Yeah, you remember. Good.
Then
Good.
don't change the state of radiation enough to account for the information.
Exactly. That's the claim.
That's what contrasts a black hole horizon with, say, a lump of coal.
Yes.
So how does this relate to?
It is. It's all going to tie together, but you gotta let me get there. But that's a great question. We're going to spend the last third of the talk looking exactly at Latour's theorem and how these effects modify the conclusions of Latour's theorem. If you're an impatient expert, I will just say to you that Latour's calculation is done in a particular semi-classical background. And when you put in all these effects, you end up in a superposition state, which includes multiple semi-classical backgrounds. And Latour does not consider entanglements across those different semi-classical spacetimes. So we'll get there. Okay, so all right, I'm glad you're asking these questions. So okay, so this is getting back to this question of, let's take a compact source and let's just deliberately, not saying this is a realistic situation, but let's just on purpose put it in, just ask, okay, let's suppose it's in an energy eigenstate, then what can I conclude? It turns out the answer to that is not original to us. That was already known. And in fact, it was known in analogy all the way from QED. So imagine that I have a source in QED which has total charge capital Q. And I want to create the photon, I want to write out the photon vacuum state, which includes that Coulomb, which includes the Coulomb potential. You can think of it as the quantum state corresponding to the Coulomb potential of that source charge Q. It turns out if you carefully quantize U1 gauge theory, keeping in track of the Gauss law constraint, you get this answer. And so one can write the photon vacuum state in the presence of charge Q in terms of the photon state in the absence of any charge using this coherent state operator. Little q is a Fourier transform of the Coulomb potential. B dagger k is a creation operator. It's a linear combination of the creation operators of the non-propagating components of the photon. So it's depending on your gauge, it's a temporal and longitudinal modes. And the charge capital Q appears explicitly here. Okay. Now it turns out you can do exactly the same thing. So imagine that you have long wavelength quantum gravity and you go through the same canonical quantization procedure that you did with QED. You can derive exactly this expression where the energy eigenvalue here, E, appears instead of Q. And this B dagger is a linear combination of modes which are non-propagating graviton modes. The important aspect of this for the logic that we're building here is that the quantum state describing the gravitational field of this compact object, which has energy eigenvalue E, it explicitly depends on E. Okay, so if I consider two levels of, so I have a rock, and maybe because this rock has Avogadro's number of degrees of freedom, the energy level splittings are extremely fine, right? E to the minus, Avogadro's number, maybe energy splittings. I could ask the question, what happens if I swap a rock with energy eigenvalue E with another one that has E prime, and there's just a tiny split? What happens to the quantum state of the gravitational field? in normal semi-classical gravity, we never ask that question because both of those states are so close together in energy. From the classical perspective, they have the same energy. But what this tells you is that if I did swap rock 1 out and put rock 2 in its place, it would be a very subtle modification of the quantum state of the graviton field that it produces. Okay, so that's an important result. Okay, this comes just from the constrained quantization of either gauge theory or gravity. There's another way to get this through something called the double copy relationship. Now, back to your question, let's take a more realistic object. Let's suppose we're not restricting attention to an energy eigenstate. Let's suppose I have a compact source, but it is in a semi-classical compact source. And so it is this energy eigenstate basis is a complete basis. So I can choose to build my more general state, the semi-classical state, as some superposition of these energy eigenstates. Generally, if it's semi-classical, that means it's the support of these CNs is concentrated in some energy range. Okay, and it doesn't have to go to 0 exactly outside that range, but it's concentrated in some range. And then generally, that's what we would that's what we're talking about when we say it's a semi-classical rock. Okay, but then I can just run the result from the previous slide, and the quantum state of the gravitational field sourced by this object is a superposition of the earlier ones, the earlier coherent states that I wrote on the previous slide. Okay, so this is the more realistic counterpart. Okay, now, I don't know if anybody in Amsterdam does effective field theory, but when I describe this kind of thing to particle physicists, they generally think many people just guess the answer. They think it's obvious. And let me explain why. So people who do real particle physics are used to thinking of complicated composite objects like a baryon, 3 quarks in the baryon. How does a long wavelength photon couple to the baryon? Well, at leading order, the long wavelength photon couples to the total charge of the baryon, right? Everybody knows that. It's not sensitive to the details of what's going on here. It just cares about the total charge. You could ask a similar question. I have some complicated composite object. It's coupling to a long wavelength perturbative graviton. What is that coupling? If I did this scattering process, I did Compton scattering, where I have my source, I treat the source fully quantum mechanically, I treat the graviton fully quantum mechanically, and then I do Compton scattering. What is the coupling here? People who know effective field theory just say the answer. It's the energy eigenvalue of this thing. That's what appears at that vertex. Everybody else has forgotten this, but it's kind of obvious. Okay. So that's the full content. That's a summary of the last few slides. It's basically just these 2 pictures. Okay. Let me talk about the effective action calculation. So back in the 1980s, people computed the one-loop effective action of quantum gravity. And so these expressions have been known since the 1980s. This is in a curvature expansion, so you have increasing powers of R. The coefficients C1, C2, and C3 are divergent. So you cannot match this low energy effective theory to real quantum gravity unless you know the UV completion. So you need to know the UV completion to get these coefficients. These non-local terms depend on alpha, beta, and gamma, but alpha, beta, and gamma are determined purely by the low energy particle content. So of the massless degrees of freedom in the model. That includes for sure the graviton, but it might include a photon or a massless neutrino or something like that. So anyway, this effective action has been known for a long time, but only in the last decade or so have people figured out how to do actually correct calculations of physical quantities using this thing. And it's very tricky because you can tell that you're doing the right thing when you get the renormalization group invariance to cancel in the physical quantities that you want to compute. People had tried to do calculations, but either they made some technical error in the way they treated this non-local term, or they didn't, they maybe only used part of this effective Lagrangian effective action and generally obtained sort of incorrect results. But my collaborator, Xavier Calmet, and his group has been working on this for over a decade. So now they actually are quite expert at making these calculations. Okay, so let's take that effective Lagrangian it includes explicit quantum corrections from, say, graviton loops, and ask, does it change any physics? Okay, so let's take a classical, semi-classical dust ball source. So it defines some TV new in some compact region. And we know the solution to the classical Einstein equations in that, for that choice of TV new. We know what that is. That's the gravitational field of a dust ball. But then we can use the modified Einstein equations you get from the effective action to see what corrections are in there. And the source of those corrections are explicitly quantum. So they all come with H bars. And so the leading thing that we find is this r to the -5th correction. And as I mentioned, the coefficient of the r to the -5th term depends on integrals over the internal density of the dust ball. So two dust balls with the same mass, both spherically symmetric, but with just different distributions of dust, lead to different potentials. And that does not happen in classical GR. Okay, but you can think of this as an example of a quantum effect when you try to treat gravity quantum mechanically, which allows there to be information far from the compact object about the internals of the compact object that you wouldn't think were there if you just invoke the No Hair Theorem. Okay, so just another example of quantum here. Okay, so the only logical ingredient that I'm going to use from all the stuff I've said so far is just that the quantum state of the gravitational field of the black hole can depend in particular on the energy eigenvalue of the state of the black hole. And if it's a superposition state, then it can depend on that various values of E of the distribution C sub n. Okay, that's the only logical piece that I'm going to take from the earlier discussion. I mean, quantum hair is an interesting thing all by itself, or quantum mechanical violations of the classical No Hair Theorems. Those subjects are interesting in and of themselves, but the thing I want to take from that is its impact on the information problem. Okay, so now I'm going to walk you through the Hawking evaporation of a black hole into n radiation quanta. And this discussion over the next couple slides is only complicated because there's just a lot of notation. It's not, we're not going to do anything conceptually tricky here, just notation, just bookkeeping. Okay, so we have this big black hole. It's evaporating very slowly over billions of years, and ultimately it's going to evaporate into exactly n quanta. That's an assumption; it doesn't have to be the case. It could evaporate into n+1 or n+2, but just for ease of notation, let's assume it evaporates into exactly n. This exhausts. Let's suppose this exhausts the full set. Okay. Now, each of these Ri is a stand-in for all the quantum numbers that the individual quantum can carry. So it's energy delta, momentum, spin, charge, everything. Okay. And so a final radiation state is specified by some list of these R1 through Rn. Okay. So now we want to define a set of quantum amplitudes. So let alpha be the amplitude for a black hole in energy eigenstate E to emit a particular quantum with quantum numbers R sub I. Okay. So it's an amplitude for emission of this quantum from this external state describing the space-time outside the horizon. Okay, and we know what this is at leading order. At leading order, it's just what Hawking calculated. Okay, but people have always suspected that there would be, or always knew that there would be corrections to what Hawking calculated because he was calculating in the leading semi-classical order. Okay, so people always suspect, or always knew actually, that there would be two types of corrections. One could be power law in 1 over the entropy. We write entropy because it's fancy, but really just means like down by powers of the mass of the black hole. And you could also have corrections which are exponentially small in the mass of the black hole. Okay, and no one knows what all these corrections are, but it's plausible that these alphas, since they can depend on this E through the quantum hair, that they will depend at some level on this E. And that's the only new ingredient in this calculation. Okay. So the fact that these corrections can depend on the internal state of the hole, which is manifested in the quantum hair through E, is the new ingredient. Now, for experts, it was shown about 10 years ago that because the Hilbert space of the radiation states is so large. If you start with the Hawking radiation state, which looks purely thermal, it's a maximally mixed state, it has maximal entropy. So that when you take the density matrix describing the Hawking state and you take trace rho squared, you get something which is nowhere near 1. Even though that's true, I can, by sprinkling e to the minus s corrections throughout this gigantic density matrix, I can, by choosing them to put them in the right place and with the right coefficients, I can still make trace rho squared equals 1. So it's been known for some time that even exponentially small corrections could, in principle, unitarize the evaporation, could make this apparently mixed state into a pure state. Okay, that remark is kind of for experts. Okay.
Sorry, can I ask another question?
Yeah.
If you go back to the previous slides, why would the properties of the quanta only depend on the energy eigenstate of the black hole and on the superposition of states of the Graviton fields?
Oh, so this is in particular an emission from the energy eigenstate. So if this amplitude is defined as if I have the black hole in an energy eigenstate, and I want to compute the amplitude to emit a particular Ri, that defines alpha. Okay. But you'll see in the expressions that we get, you're going to get sums over alphas weighted by different CNs for the semi-classical case.
But no different keys.
No, so sorry. So CN, the N labels different energy eigenstates.
Okay.
So you'll see. Okay. So now I'm just going to walk through having defined all that stuff, I'm just going to walk through the evaporation of the black hole. So psi is the initial quantum state of the external geometry outside the horizon. Because the black hole is in this semi-classical superposition state of different energy eigenstates, I write this. I have to write this sum over C sub n's, and this G now is just the Dirac notation version of what I was writing before as psi G of E. Okay, but you see the argument is E sub n. Okay, so this is just a translation of what we wrote earlier into more of a Dirac-like notation. Okay, now let's emit the first quantum. So I'm going to emit one quantum labeled Ri. I have to sum over all the possible states Ri. The amplitude is the amplitude to emit that thing. The external state outside the black hole changes to the external state appropriate to a black hole with energy En minus the energy of the quantum that was emitted. And then I record that the quantum is out there too. Okay, so that's what this notation means.
So aren't you assuming infinity then? From pure state to pure state?
Yes, exactly. So the question is, if I didn't tell you this was a black hole, I said, okay, I have a very complicated molecule. Okay. But the process where this quantum is being emitted or the pair production is happening, okay, is happening in the background, which depends on E. Okay. What would you write? You would write a quantum transition amplitude, which is itself a function of that background condition to emit the quantum R1. Right? So the logical change that has happened here is that in the past, people said, well, there's the horizon. So somehow this R1 is produced. R1, the amplitudes for these R1s can't depend on the information that's behind the horizon. But if this amplitude can depend on the quantum state of the gravitational field, then you write an expression like this. But you're right, the unitarity is right there. Right? This is a unitary quantum process now, and it can be because the information describing the quantum state of the black hole is present outside the horizon. Okay.
That seems like it's assuming the answer.
It does give you the answer. I mean,
But you're assuming the answer.
well, if I tell you that, let's suppose I have some very complicated like why would, let's suppose I have a complicated molecule that's ionizing. Okay. This is the natural expression you would write. Okay. Now, why would you not write that for the production of a Hawking quantum? Because someone told you that the space-time just outside the horizon where the fluctuation happens doesn't know about the quantum state inside. But that logical condition, which is extremely strong, is actually not true. So this is a big change. I mean, once you, in a way, you're totally correct that once you accept this step, everything else is going to follow trivially. So it is a big step that you should think about. Okay. You could also ask yourself, if somebody, suppose some crazy guy in 1976 came to you and said, I have this amazing theory. I'm a brilliant guy. I have Lou Gehrig's disease, but I'm a super genius. And I've studied the burning of coal. And I've decided the burning of coal is not unitary. It causes pure states to evolve into mixed states. And then he challenges you to prove that that's not true. Well, how would you do it? We don't have enough control, theoretically, to analyze the burning of coal. But we allow ourselves in the burning of coal to make steps like this, or in the ionization of a huge molecule. We allow ourselves to do it. But there better be a damn good reason why I can't do it. But I just showed you in the earlier slides that reason is not true. So that's the key step here. Okay. So, but for everybody else, let me continue through and just walk it through. Okay. So now let's emit the second quantum. Okay. So what happens when I emit the second quantum? I take this state and I'm going to end up with a second quantum. Is the second amplitude. That amplitude is now a function of En minus delta 1. And the properties of quantum are 2. And now I sum over not just the possibilities of R1, but the possibilities of R2 as well. Okay. And so you can see trivially, I just end up with some expression like this. At the end, I don't have a black hole. So this state is just describing the quanta in the radiation Hilbert space. There's no black hole left. These CNs have gone through the whole calculation. And so the answer is linear in the state of the original black hole, which in quantum mechanics, that's what it's supposed to be, right? So that remark was correct, that once you take the step, every other step is like it, and then you get unitary evaporation. Okay. So I guess I already said that. Now, you'll notice the final radiation state, it's a complicated superposition state. It depends linearly on the initial black hole state, those CNs. And under time reversal, it's trivial to see you can go back to the original black hole state. And in particular, if you, in principle, could compute these alphas, once I told you the state, suppose you did perfectly accurate measurements of this external radiation state, you could back out what these CNs were, and then you'd know the exact state of the black hole. Okay. All right. Now, I said something about macroscopic superposition states. So let's look at different radiation patterns R1 through Rn. So it could be that R1 was a photon and it went left, but it also could have been an electron that went right. Okay, so they're very, very different states inside this list of possible radiation patterns, and they lead to different recoil trajectories of the black hole. So the black hole is going to convert all of its rest mass into radiation, and it's going to take place over an incredibly long period of time with very, very many different possible trajectories. And you can calculate the uncertainty in the final center of mass coordinate of the black hole, and it's macroscopic. It's actually m in Planck units larger than the original Schwarzschild radius. Okay. So what happens is that the black hole is recoiling, and because there's so many different possible radiation patterns, you must end up in a superposition state of very, very many different trajectories of the black hole, of very, very different spacetimes. Okay. You remember, to get to one of these Penrose diagrams, we have to make a bunch of coordinate transformations where we always put the black hole at the origin of those coordinates. And if the black hole is over here and going to the right, it's very different from the black hole being here and going down. Okay. And this conclusion doesn't depend on any of the new stuff in the talk. This is already just implied by the leading order Hawking calculation, because in the leading order calculation, these are just draws from a thermal distribution. So you have to get all these possible weird trajectories, potentially. Okay, so here's a little picture. If the pattern has more stuff going this way, the black hole has to do this. If the pattern has more stuff going this way, it has to do this. And over time, you have essentially actually just a Brownian recoil random walk with this black hole. And they're all in the expression that I wrote contains all of these things. So there's a translation between a given choice of this pattern and a particular one of these trajectories, and therefore a particular macroscopically different spacetime. Okay, so all of that's in this description. Okay, so let's come to Matur. So if you remember, Matur claimed that he could give an argument where as long as you only allow some perturbative modifications of the standard description, of the Hawking description, you could not restore unitary, you could not restore purity. Now, you objected when I made that unitary step, but that unitary step is what Matur would call an epsilon correction, because my alphas only have to be epsilon different from the Hawking alphas. So the question is, how does this evade the Matur theorem? Okay, so there are two separate questions. You can certainly object and say, I just don't allow you to unitarily omit the first Hawking quantum, right? You have to judge whether that step is okay. But even if you accept that that step is okay, you have to scratch your head and say, wait, how did he escape the Matur argument? So that's what I'm going to talk about now, okay? So what Matur said in 2009 was, because we know, okay, so if you're a freely falling observer and you fall past the horizon and it's a very big black hole, there's maybe a little bit of tidal force, but not much. Very little deviation from the vacuum state of flat space. We know that vacuum state very well. We can conclude that the fluctuation that leads to the Hawking quantum that escapes originates as a highly entangled pair. Written in his schematic notation, that means that the state of the mode that gets absorbed by the hole, those are the E modes, is highly correlated or perfectly correlated with the state of the escaping mode. Okay, so it's a highly entangled state, and eventually you lose track of the E modes because they hit the singularity. Okay, so again, modes which are going to escape to infinity are B, modes which are going to fall through and hit the singularity are E. Various arguments for why it has to look like this. And if I eventually am going to be forced to trace over these E's, then the entanglement entropy has to go up by log 2. Okay. That's the basic setup. Now, if you remember that the time, there's millions of years potentially between the emission of the first quantum and the next quantum and the next quantum. So plenty of time for the vacuum state to settle back down. We know what's going on. We can reliably state that at each step, until the very end, where you have a Planckian black hole remnant, Planckian black hole, that's a strongly coupled process. But every other emission of quanta, one can argue has to look like this. Okay, so he gets this highly factorized description, and when you calculate the total entanglement entropy of this thing, when you force me to trace over the E's, you get something which is proportional to the number of quanta that were emitted, and you get log 2 for each step. But he argues that if you allow only weak corrections to the Hawking picture, all you can do is change this log 2 to log 2 minus epsilon. You still have a big problem. So you still have a pure state, potentially, which evolved into something that has a huge entanglement entropy and is described by almost maximally mixed density matrix. Okay, so that's the Matur argument, which I think is very conceptually clear, because the physical assumption that's just been made is that we know the physics at the horizon when the black hole is really big. That's basically what's being assumed. Okay. And then there's further steps to show that all of the perturbations he could think of to his setup didn't really change the answer very much. Okay. All right. So why is the picture that I gave earlier different? Okay, so if you look at what Matur is doing to define the E mode is a little fluctuation around the vacuum state in near the horizon of the black hole. But if I have two very distinct patterns, B and B prime, those regions of space-time are actually completely different. So I could have the black hole over here, and I define an E mode that's about to get swallowed. But for another choice of earlier emissions coming from the hole, the black hole is actually over here and has a completely different velocity. And the E excitation here is not the same as the E excitation here. Okay, so it's clear that the formulation that he gives does not consider at all any possible entanglement between the geometry that's implied by this radiation pattern and the geometry that's implied by that radiation pattern. He just has a radiation, he just has a particular radiation pattern, and then he calculates the entanglement. Okay. So if you look at our expressions, which I'll put back up in a second, there is no factorization. Because those alphas are connecting different possibilities in the way the modes are emitted, it's not factorizable at all. It's not even approximately factorizable. So it doesn't look like his product state. The moral equivalent of his E modes are the following. So when his E mode gets absorbed, the black hole back reacts and there's a decrease in its energy. But in our case, that decrease in energy is reflected in the quantum state that is the environment for the next emission outside the horizon. That ingredient is not present in any of his analysis. It is present in our analysis. This state, which is the kernel of his construction, its moral equivalent in our analysis is that, okay, we don't track these E modes, but we track the quantum state of the exterior graviton field. Okay, and yes, there is still this entangled structure. But when you look in our, so this is just the slide I showed earlier. If you break this open, because this includes ultimately all the patterns allowed of the Hawking radiation, you'll see that it contains many copies of his factorized states, but then there are entanglements between those copies. So what he says is strictly true, that if I condition on a particular space-time background, that defines a subset of these radiation states. And the entanglement entropy generated conditioning on that subset of these radiation states is huge. It grows like that. But when I look at the full state, which is pure, I see actually that's not true. When I calculate everything together, the state has remained pure through the whole evolution. Okay, so that's the difference between the description here and the Matur's theorem. Okay. Now, I'm going to make a comment for the experts. So there's a phenomenon which is better known in mathematics. It's known, I mean, it's originated in probability theory and high-dimensional geometry, and it's called concentration of measure. But in the last 15 years or so, physicists have realized that everything that we know about quantum statistical mechanics, or at least equilibrium quantum statistical mechanics, can be derived from this property of concentration of measure. Concentration of measure is talking about the properties or the geometry of high-dimensional spheres. So if you think of a state vector in a very high-dimensional Hilbert space, because there's a constraint on the norm of that state, it is basically just a big vector that's constrained to lie on a huge high-dimensional sphere in a complex vector space, okay? So it turns out that your intuition about spheres from low-dimensional spheres is completely wrong. And in fact, all of the measure in a high-dimensional sphere is concentrated in a sense around its meridian. The way to think about this is that if I have many, many different entries in this long vector, but the sum is forced to be 1, there's a very typical way that these coefficients can arrange themselves. And you very seldom find, like if this is a particular coordinate, a particular component, you very seldom find one of these guys taking up most of the norm. The norm is spread amongst a bunch of guys. And so anyway, the measure on a high-dimensional sphere is highly concentrated. And that means the measure in a Hilbert space is highly concentrated. So there's a lemma, a very famous lemma in mathematics called Levy's lemma. And from Levy's lemma, you can rederive everything in quantum statistical mechanics. And one thing you can derive is that, so let's take it back now to the black hole issue. Let's suppose you have a very big Hilbert space, which I'm going to call Y. And Y is all the possible radiation patterns that can come from a big black hole. And then let me consider subsets X of Y. And let me define the subsets to be particular radiation patterns which are consistent with one specific recoil trajectory of the black hole. Okay, so I would claim that's what Matur is considering. Okay. What Levy's lemma says is if I choose any pure state in the big Hilbert space Y, and I compute the density matrix of that state restricted to X. So I look at the small subset X that I defined, I trace over the complement of X. The statement from Levy's lemma is that this density matrix will be very close, exponentially close to maximally mixed. So in physics language, that says if you restrict yourself to considering only a subset of the radiation patterns or only a subset of the recoil trajectories, you must find a maximally mixed, highly thermal result. So it looked like not a pure state, even though you got there by restricting something that actually was a pure state. Okay. And the thing that when you take that trace to get the density matrix, what you're doing is you're tracing over these entanglements between different X's and X primes. Okay, and that's why you get something that appears to be maximally mixed, even though secretly what you're dealing with, if you could see all of it, was a pure state. Okay, so, all right, let me stop here. So, okay, what are my conclusions? Well, classical No Hair theorems do not extend to the quantum realm. The quantum state of the graviton field outside a black hole actually does carry information about the interior state. You can deduce these results without knowledge about the UV completion of gravity. These are properties just of long wavelength quantum gravity. We can describe Hawking, the evaporation of a black hole through amplitudes which differ just slightly. They only have to differ very slightly from Hawking's semi-classical results. No exotic new physics, no weird non-locality at the horizon, nothing like that is required. Standard formulations of the information paradox, I gave you multiple ones during the talk, are always implicitly talking about one Penrose diagram. So they're actually talking about one particular background geometry, which is a small subset of the possible background geometries which could actually be involved in the full process. And they neglect, in particular, the entanglement between different space-time geometries. Okay.
Questions for Stephen at the end of the talk?
Yes.
Like you use, or you say it is sufficient to have small deviations to these coefficients, right? To the
Yes.
transition.
Yes.
That's true, but you need that a large number of them is different than the ones considered by Hawking,
Yes,
right? That's
correct.
the trade-off.
Correct.
But so what I don't see is like, how do you get the, like, what this means, I understand is that, like, as you just said at the end, you should actually think that this wave function of the universe or something like this is like a superposition of many different states, which differ by the details of the sort of density function inside the star or something like this.
Yes.
But could you tell us something about, at the classical level, like, what is the distribution? Like, what is the standard deviation of this? Like, why don't we see this in
Yeah. So, okay, great question, but there are about 3 questions in there. So let me go through them. So first, this comment about to what extent these alphas need to differ from the leading order Hawking calculation. The leading order Hawking calculation is a semi-classical calculation. So if I change this delta 1 to some delta 1 prime here, semi-classically, those would, to Hawking in the limitations of his calculation, those would really be the same semi-classical black hole, right? Just shifting the energy levels by e to the minus s of the black hole. I mean, the energy level spacing in this black hole is e to the minus s, okay? So if I just shift the energy levels a little, I'm still talking about the same classical black hole. And so his alphas just would not have this dependence.
But you need a large number of them.
Right. So you have a large number of them, and each of them is just slightly different. So the argument that I said, I didn't prove it, but this argument's existed for over a decade, that even if they're maximally small, e to the minus s corrections to the Hawking calculation, it's enough to unitarize. It's enough to, if you modify the density matrix, you sprinkle e to the minus s's in the right places. In that maximally mixed 1 over n, 1 over n, 1 over n, 1 over n density matrix, which you get from Hawking, you can still get something which satisfies trace rho squared equals 1. So that's been known for a long time. So the required size of the deviations of each of these alphas from Hawking is extremely small. And it could even be like people like me 20 years ago would have said, well, those could just be non-perturbative quantum gravitational effects, like little wormholes, or could be anything. So that was kind of already known, but nobody really knew what would cause those e to the minus s corrections. Okay, so that was to address your first thing you said. Now, if I come back to, so people, generally the thing people object most to is about the last part of the talk is they just don't want to think about macroscopic superposition states. Even though in the lab over there, they're, well, maybe not there, but somewhere they're making macroscopic superposition states right now, okay, of actual bugs, tardigrades, and things like this. So people don't like to think about it, but it's becoming part of physics, okay? So now, I'm not making any statement about many worlds quantum mechanics or things like this. I'm just saying, if you're bold enough to ask the question, does the presence of a black hole here not allow Schrodinger evolution to be unitary here? Then you have to let me actually use no collapse Schrodinger evolution here to see what happens. But when you do that, you do end up with macroscopic superposition states. So the way we get out of it usually is we say, if you're from Copenhagen, then you say something like, well, at some point there's not there, the wave function collapses, that's it. So that's an interpretational question. But if we are talking about whether the initial data on this blue space-like surface can unitarily evolve from here to here and back, you can't collapse anything on me. You have to just let me, run it forward and run it backwards. So you do always end up with macroscopic superposition states. There's no avoiding it. But it's not a claim about, though, how to interpret quantum mechanics. It's just a claim about the mathematical result of taking this problem and evolving this forward. Does that help? You can ask more questions.
I can ask you later.
Yeah. Yes, sir.
Was it important in your discussion to assume that these psi sub g of E were a complete basis?
No, I don't think so. It was important that we had a complete basis describing the internal state of the black hole. But it was not important that psi g of E be a complete basis. I haven't really thought about whether it should be or not.
Well, if it's not, did your alphas depend just on the G then, or was it semi-classical computation?
Yes.
So your alphas only depend on the G. So if psi sub G of E is not a complete basis, then this process would not be unitary, I think.
Oh, I'm sorry. You're talking about these expressions.
Yeah.
Yes.
If this G of En is not a complete basis, then there's no, and the alpha depends only on this G, then it's not unitary.
I have to say I haven't thought carefully about what is the right statement about the psi g of E basis. But
Well, I think it's important because if that were a complete basis, then you could just by quantizing semi-classical gravity, looking at the phase space, you should find enough degrees of freedom to get the black hole entropy out. That we believe does not work. So we don't believe that this is a complete basis. And there's clearly a complete basis in some bigger Hilbert space, but there is no complete basis believed to exist in the gravitational phase space. And if alpha only depends on that metric, then information gets lost in this process because it erases some information from these microstates, unless this is a complete basis. So
I need to think more about your question, but yes, it's a good question.
Okay, any more questions for Stephen? Yeah.
Even in Hawking's calculation, I think that I understand what you're doing. Wouldn't the these alphas or the emission probabilities of depend on the energy of the black hole, or they definitely depend on the temperature, which is related to it.
Yes, but in his calculation, he's not sensitive to a very small shift because he's always treating the black hole semi-classical, the space-time semi-classically. So there's just not enough precision in that calculation. So we can pretend that we can do that calculation, and then you can get these fine dependencies. But we can't. It's certainly not in his original calculation. Can you find that?
Right, but even if you just took the tree level action and applied what he was doing, but just apply it over a very long time, you would still get something like this, wouldn't you? Because the over time, if you include any kind of that action over time, the mass of the black hole, therefore the temperature would change, and therefore these alphas would change.
So, not exactly sure which what hypothetical calculation you have in mind, but in the approximation where there's a long time between these Hawking emissions, and you let the horizon vacuum region settle back down to something like its ground state, then you really have a problem because, at least in this description, you can't avoid producing these highly entangled pairs and then just having the entanglement entropy just grow and grow and grow.
But over time, the temperature of the black hole changes, and therefore the Hawking temperature changes. So it's not like if you wait long enough, clearly these emission rates will change.
The emission rate, so I mean, in the semi-classical picture, there is a temperature and it's slowly decreasing.
Yeah.
But the temperature by itself doesn't contain enough information to, for example, tell you what came out in the last step. You see what I mean? It's too coarse a variable. It is decreasing the temperature and the mass of the black hole, but at least
it contains the energy, which is the same thing as your alpha.
No, yes. So if you accept the notion that the detailed properties of what lies just outside the horizon can depend on the actual energy eigenvalues that characterize the black hole state, then you can definitely get all this. I mean, I'm advocating that you get all this stuff, but if you don't accept that, then you don't get it. And the way you pass from ordinary semi-classical gravitational calculations to treating the source in a fully quantum mechanical way is, as far as I know, not something everybody agrees on or has been worked out in detail. But I'm not disagreeing with what you said, but I'm saying
No, I agree that the step of taking into account, in some sense, the back reaction and looking at the state of the black hole itself is something that changes with time. I agree that is an important ingredient. What I don't quite get is how does taking the subleading terms or the one move terms in the action.
okay, good. Okay, sorry. So that probably what I said was confusing. I said this in a confusing way. So when we did this calculation, we did not mean this to actually play any role in the subsequent analysis of Hawking evaporation or unitarity of black hole evaporation. This was just a particular calculation which is actually under theoretical control, which shows that the standard picture of what information is contained in the gravitational field of an object in classical physics is not correct when you quantize the theory. That's all this is a demonstration, but an actual calculation you can do, which shows that these classical ideas that, oh, there's a horizon and there's nothing you can know about what's behind the horizon is not true, actually. You can know things about the internal state of the dust ball, which collapsed to form the black hole. So yeah, that's all this is. But there's much more than just this one loop calculation in the further analysis.
From the examples you gave, what you seem to be able to know is the energy.
Yes.
But that's something you can already know, because the energy determines the temperature.
I know, but we normally, that temperature is normally a semi-classical thing that we're talking about. So we don't claim to know it with absolute precision, right? So just as we don't claim to know the mass of the black hole to e to the minus s precision, at least not in Hawking's calculation.
but over time it will definitely change.
Of course, I totally agree with you. But by the way, I mean, the thing you're saying is also what I said was kind of trivial for people who are used to effective field theories, that the energy eigenvalue of this incoming thing is going to play a role in this vertex. So yes, it is true, but I don't think that's in any of the previous calculations of black hole value.
Okay. Well, if you have no more questions, let's start. Thanks, Stephen, again for your talk.